What else? The electromagnetic spectrum. All right? The electromagnetic spectrum, y'all, is the way that it's like, this is an order, and you have to know this. It's a great picture in your book, too. There's a great diagram. But it's in order from the longest wavelengths, okay, to the smallest wavelengths or shortest wavelengths. And then the opposite, because if it's a long wavelength, it has a low frequency. If it's a small wavelength or short wavelength, it has a high frequency. So that is why you have to understand these in order. All right? You don't have to memorize the values, but you have to memorize the order or learn it. Okay? And the first one is radio waves. Okay? And there's AM waves have longer wavelengths than FM. Okay? So FM has a higher frequency than an AM wave. All right? Because remember, lowest frequencies to highest frequencies. It's just like the periodic trends we did. Okay? You got to know the trend. You got to know the order. The next one that comes in line with the wavelength is microwaves. All right? Then the next one is infrared waves. What is infrared? You guys are playing little video games. All of a sudden, oh, got the night scope, right? I can see the heat signatures of the people. That's infrared. All right? So, microwaves, what do we use those for? Yeah, heat up our food, right? And then radio waves, obviously we listen. What else is radio waves used in? Cell phones, walkie-talkies, right? Okay? Now, they did an experiment back in the day, you guys. They took a picture in like 1980, okay? And they showed like the amount of radio waves that were in the sky. And it was like really not hardly any at all. It just looked like that. And then they said, okay, 1990, okay, what do the radio waves look like, right? And it was, you know, a little bit more, not as much. And then after the 90s, really cell phones started coming out. So then they did it in the 2000s, okay? And it was more, I mean, this is like in the sky above us, right? Okay, now what do you think it looks like? It's just black. Like there's so many radio waves going through the sky and going through the, take your earbud out, Jack. Okay, we're not Secret Service in training. Okay, so it's like black. Well, you guys, we don't know what the long-term effects of that's going to be on your brain. I hope we don't all get cancer when we're 60 because we've had an absorbent amount of radio waves going through our brains for 50 years because we're on our cell phones since we're 10. Okay? But we don't know the long-term effects. It might be like when we get to be, 60, they're like, wow, that was a mistake. We just basically gave everybody cancer agents and held them up to their faces for 45 years. Okay? So hopefully that's not going to be the case, but you never know. Here's the other thing. The next wavelength. You get radio waves, microwaves, infrared. The next wavelengths we can actually see. Okay? And that is visible light. Those are the colors of a rainbow. Very important that you understand the order also, because it directly correlates with this. Roy G. Biv is the colors of the rainbow. Red, orange, yellow, green, blue, indigo, violet. Red has the longest wavelengths and the shortest frequencies, just like radio waves have the longest wavelengths and the shortest frequencies, or lowest frequencies. Violet, and it's in order, violet has the smallest wavelengths, okay, and the highest frequencies. So just like this corresponds in order, so does the rainbow. All right, so on tests, I might say, put the colors in order of the shortest wavelengths to longest wavelengths. And if I give you orange, green, and indigo, you'd have to tell me that orange has the shortest, then green, then indigo. If I say which one has the highest frequency, green, blue, or yellow, you would say blue has the highest, then green, then yellow. All right, so you have to be able to put them in order with that trend. So it is important, okay? You need easy test questions to be made off this. Now, after visible light comes ultraviolet rays, then X-rays, then gamma rays. All three of these will kill you, okay? So it's important to understand that as the frequency of the wave is increasing, the energy also increases. So frequency and energy of waves go hand in hand. The higher the frequency of the wave, the higher the energy in the wave. So which one has a higher energy, X-rays or radio waves? X-rays, because it has higher frequency, it has higher energy. Ultraviolet's what we get from the sun, that's what will give you skin cancer, right? X-rays are what we get from the dentist. That's why you wear the lead jacket. So you try to avoid as much of it as you can. Like they zap your face, okay? And a little bit's not going to hurt you probably that much over time. But if you were getting zapped constantly with X-rays, you would get cancer in your face and you would probably die. Okay? Gamma rays, that's radiation. Okay? When there's nuclear meltdowns, it's giving off gamma particles. That will definitely kill you. Okay? Chemotherapy. Okay? That's gamma. I mean, we're chemo, basically, you're just radiation, you're hitting that cell, that area of your body, and it's just killing everything in it, trying to kill the cancer cells. What else is gamma rays used in? Weapons. The average lifespan of a tank in war, back in the day, in World War I, tanks were it. I mean, it was like you would roll in and you were like unstoppable because bullets couldn't hurt you, right? I mean, you had to like climb on top and throw a grenade in and couldn't kill it. Now they've got tank buster missiles. They paint that thing with a drone. Okay, I mean, you're an Iraqi and you're, going in your tank and you're thinking you're all that. The average lifespan of a tank in modern warfare is 3 minutes. Okay, because they will paint you and that missile hits the side and it sticks to the armor. The gamma radiation melts the armor, delivers the payload, and blows it up. Okay, yeah. So gamma radiation is used in weapons also. So it's pretty cool. All right, so. Electromagnetic spectrum. You need to know it. You need to learn it. Okay? This is the order, okay, that is in from the longest wavelengths, which is lowest frequencies, to the shortest wavelengths, which is the highest frequencies, okay, of waves. All right? So what do we talk about with the the speed of light? That is, if I'm given a wavelength, I can find the frequency. If I'm given the frequency, I can find the wavelength of a wave. All right, using the speed of light, which is a constant. All right, well then Planck came along. I told you that's wave, so that's Schrodinger, right? Planck came along and he did the photoelectric effect, which he shined light on metals and noticed that they were giving off these particles. Okay, he called those photons, right? And later they found out that those are little packets of energy being given off, which are called quanta. And we're going to see that in quantum mechanics. They define that in the atom. All right? So what was Planck's formula? Well, Planck came up with the energy of a particle. Okay? So Planck's formula is E equals hv. E is the energy of a particle, and we use the unit joule. Okay, so it's the joule, and it's a big capital J. His H is Planck's constant, which is 6.626 times 10 to the negative 34 joules times a second. I will always give you that constant. You do not need to memorize that, but you do need to understand how to use it. Okay, that is the unit given, for 1 photon of energy. Okay, that's what Planck came up with. 1 photon of energy one photon has that much energy. Then, the frequency, okay, is V. We already talked about that in our other formula, right? And the unit is 1 over a second. So, the formula is energy equals Planck's constant times frequency. So, if I'm given frequency, I can solve for energy. If I'm given energy, I can solve for frequency. Does everybody see that? Yes? Because you're going to do math problems with it in a minute. All right. Well, the last thing is this. How do I relate the energy formula with the speed of light formula? What variable is in both? V, which is frequency, right? So what you're going to see is they're going to give you the energy and ask you for the wavelength sometimes. Okay, don't let that freak you out. It's okay. If they ask me for a wavelength, I'm going to use this formula, right? Wavelength equals C over V, which is speed of light over frequency. If I'm given energy, then I can solve for V. So the first step is solve for frequency, right? Given energy divided by Planck's constant, so whatever I'm given in energy, divided by Planck's constant, that gives me my V. And then I'm going to take that V and plug it in here and take the speed of light divided by my V, and I can get my wavelength. Okay? Now the other step they might do is they might give me the wavelength and ask me for the energy. If they do that, then I first I'm given the wavelength, so I take speed of light divided by the wavelength to get my frequency. Then I plug my frequency in here and multiply it by Planck's constant to get my energy. Does that make sense? So if I'm given wavelength, I'm going to solve for V first, and then step 2, I plug it in that formula there. All right, so that's what we're going to be practicing today. How long was that?
15.
Yeah, that's not bad. That has all of it.